Hi everyone, welcome back. So in this video, we will discuss about page cache and page writeback. So this video requires the knowledge of virtual file system and disk block I/O operations and process address space. So if you guys have not seen those videos, please watch those first, then come back. So let's get started. So in this video, we will discuss about all these things. So we will discuss about cache approaches, cache eviction strategies, and of course, we will discuss about page caches. What is that? And we will know that what is the buffer cache. And at the end, we will discuss about flusher threads and laptop mode. So now let's understand what is page cache. So before understanding page cache, let's understand what is a page inside a page cache. So as you know that we write some programs where let's say this is the example of a program. So if you see here I am opening a file and here I am writing something inside a file. So these read, write and open operations on a particular file inside a program. So we have to access that file from the disk because all the files are stored on a disk or a block device. We will discuss about disk and block device in further slides. So this is a generic example where we access different files. So because we access files, we access them in form of page because our memory management unit takes pages to map into the main memory. So that's why, like if you see here, if you access or do IO means read or write operations on regular file system or block devices or memory mapped files. So these are the different type of files where we do IO. So as we know that in Linux, everything we can represent in form of a file or uh, yeah. So we can also represent the block devices as file. We can we can represent the regular file as a file, and also we can represent some memory map devices as a file. So whenever we access a file, we keep we keep a copy for quick lookup inside a page cache. So that's why we have a page cache. So the name page cache comes from the page of a file system, and this page cache is stored into the main memory. So this is not a separate hardware we store the page cache. This is just a part of a main memory, and it is managed by kernel with the help of the memory management. So we have already discussed about the memory management in the Linux kernel. So you can go back and see that video also. So why do we need the page cache? So like if our CPU needs want to read some data from a file because it is the requirement of a program, because inside a program we are opening a file and we are reading. So every time we have to go into the hard disk and we have to get that page. So as you know that hard disk is a mechanical device and it has read write head. So it has to rotate and read and write has to come on a particular location and fetch that file. So that is a very slow process. So that to make this process very quick, because CPU need data very quickly, so we keep a cache of those recently accessed pages. So that's why this is a one reason. Also, like uh, in page we contain lot of data. So if I am accessing this data, it is a high chance that in the next cycle I will I will access some data in the same file in the next location. So this is called as temporal locality, that in near future I will mostly I will try to access the next data. So it provides the benefits of both the things. So that's why we have to keep the page cache. So I would say that you guys remember this whole diagram. It is going to be very useful in whole coming slides. So if you see here, this is a page cache. So it is built on top of a file system. So, and this is a buffer cache. So we will discuss what is the difference between buffer cache and page cache, and how it is managed inside a kernel. So, so let me tell you that every disk, whatever disk we are having, so in a disk we can have a implemented file system, and file system can be like ext4 and fat32. So these are the different kind of file systems. So in a disk we have implemented some file system, so that the content of that particular file we can view in our user space here, in this process space or user space, as it is mentioning here. So we see those files with the help with the help of this file system. So file system will try to organize the content of a disk with the help of file system, and it will provide the data in form of a page. uh, like we keep those data uh, for the main memory in the form of pages. That's why we have a page cache. And also there are, like, this is a hard disk HDD, but there can be other block devices. So like hard disk is a type of a block device. So there can be other type of block devices here, which like for which kernel want to operate on them directly. So like if kernel want to operate on this block device directly, then it will operate on this block device based on the buffer cache. So it will this buffer cache maps uh, like blocks of a block device. So if I want to operate on a block device directly from the kernel, and this block device may not have implemented any file system, so we directly do raw IO operations on the block device. In that case, kernel will directly go to the buffer cache and operate on a block device. That's why we need this buffer cache. And also, like this buffer cache, we manage with the help of page cache. So there is no need to keep the two copies of the same thing, like in the buffer cache and in the page cache. These things we will discuss in our coming slides. So if you see here, this is a read that we are issuing, and it goes to the virtual file system, and then it will search into the page cache. And then based on the page cache, if I want to write to some data to the disk, or we want to read some data to the disk, then it will tell to a specific file system. This file system can be different, like ext4 or fat32, and then it will search into the buffer cache, and then it will tell the device driver to do some operation on a device or disk or block device. So this is the organization, how flow goes from user space to kernel space and directly at the end in the device. So let me tell you how do we manage the page cache. So this whole page cache we represent with the help of a structure that we call it as the address space. So the responsibility of address space is that it manages the entry in the cache and also the page IO, because we are doing read or write. Those are called as page IO. So these are the related fields where we represent our page cache structure. So you can say that this page cache or address space. So from here, I will use page cache and address space interchangeably. So both are the same thing. So if you see here, it is a part of a inode structure that we have already studied in the virtual file system. So you can say that this address space structure is per inode. So like we have multiple files, file 1, file 2, file 2. So these files are associated with some inode. Okay, So like from in a single inode, we can have address space that represents multiple pages. Like this address space will have series of pages. So it can have multiple pages inside the address space. And these will be the cached pages. So these are the entries where we represent the address space for a specific inode. Here I have kept that picture again so that we can refer it again and again. So if you see here, it tells that from the this page cache, we can also relate it to the process address space. So why we have to relate it? Because if you see here, this is a program. When it will be built, it will be converted to a process address space that we have already discussed in the previous video. So within that address space, we are accessing a file. So from that address space, we have to jump to the page cache. So that's why we keep this information uh, related to the page process address space. So let me show you how we are relating to that. So if you see here in this structure, so these structures are related to the uh, process address space. So if you see in the VM area struct, we have this field VM that maps to the pointer to a particular file. And from that file, we can have that I mapping. Uh, and as we know that every file is related to an inode, so it will be related to this inode, and this inode already have the address space. I mean the page cache. So in this way, you can see uh, we are here in the page cache. We are accessing the page cache from the process address space. And if you see further, then from the address space, we are pointing to specific pages on the disk. So this is just a copy of the pages in the page cache. So these are not the actual disk pages because this is a cache. So let's see the further details inside the address space structure. So if you see here, this variable, I will discuss the important variables only, not all the variables. So if you see here, this is a owner, like it can be a inode or it can be a block device. So it is saying the same thing here. And this field tells us all the pages that are cached. And this structure tells us all the operations that address space can support to manage the cache and manage the IO, as we have already discussed these things here. And we have other variables that are not that much important for this video. So if you see here, this is a address space operations. So you can say that these are the all operations that we can do to manage the cache of pages. So if you see here, this is a function to tell that we have to write a page into the disk, and this is the function to read some page from the disk into the page cache. And this is a function to write if you want to write more than one page. And this, if you see here, this variable tells us how we need to write. So and all these operations are file system specific, because the pages are related to a specific file system. So these all operations should be specific to the different file system. So like this same function can be implemented differently in the FAT32 and ext4. And this is the function where we can make a page as dirty means like we have modified that page, like we have modified some value of a variable. In that case, that this page is dirty, so we are saying that we have modified this page inside a cache, but that change we have to do in the disk so that it is a persistent change. So for now, we are saying that we have done the change in the cache. Later, we will do in the disk. And that we will discuss in coming slides. And this function tells the file system that we are going to start some write. So it will prepare the file system will prepare itself for that write. After this function, we will write some data there, and when this copy or write of the data is complete, at that time we have to run this function write end. And I will discuss this another function. So if you see here, direct IO. So this function tells that we are not going to make the changes in the page cache. We have to directly make the changes in the IO mapped file or IO mapped devices. So it bypass the, it tells that we have to not make any changes in the cache. We can directly make the changes into the IO mapped device. And we have other functions also, but I have discussed here the important and related for this video. So like this statement is important. So you can see here, all the page IO is guaranteed to go through the page cache. How? So like page IO can be read and write. So whenever we are reading or writing, first we have to check the cache, because accessing disk is very costly. So whatever operations we are doing, we are checking the cache. So that means it is always guaranteed that we have to go through the page cache. There is no other option. So let's now discuss more detail about the buffer cache and how it is related to a page cache. So as I have already discussed that when we need to do some block IO operations on a disk, not a disk, block device, at that time we map the blocks of a device uh, in the buffer cache. Okay, so if you remember in the previous video of block IO devices, I have discussed that we represent a block with the help of a buffer, and that buffer is managed with the structure called buffer structure. So this is a same slide I have taken from the previous video. So if you see here, we have buffer head structure that manages the whole block of a block device. So that's the same thing I have written here. When a block is represented in the main memory, we call it a buffer. And to manage that buffer, we have a structure called buffer head. So so you can say that we have the blocks here in the buffer cache, and uh, and like in the coming slide we will discuss what is the difference between buffer like how are buffer cache and page cache related. So let me tell you that. So if you see in the x86, this is a page size. So you can say that it is a page, and the block size can be different, like it can be 1 kb, 2 kb, 4 kb. So let me assume that as it is a 2 kb block. So you can say that this whole page can represent uh, block 1 and block 2. So that means our page can represent multiple blocks of a block device. So that means like we can map these blocks to a particular page in the page cache. So in this way, we can say that like we don't have to keep the two copies of the same data in the like buffer cache and page cache. So let me further in the next slide we see. So if you see here, we have this buffer head to represent the buffer, and it will represent the buffer cache. So if you see here, like we are not keeping any data here, we are just pointing to some page descriptor. So like every page have a page descriptor. So we are just making the pointers into that. That means this the whole buffer head is represented inside a page only. So in this way, we can say that uh, like we are managing the buffer cache in the page cache only. So let's go through again here. So like if you see, page cache is for optimizing the file IO. If I want to do some read or write inside a file, then we have to go through the page cache. If I want to do some block IO operations on the block device, then at that time we go through the buffer cache. And these buffer caches can be also represented in the file system with the page cache. So the same thing I am mentioning here. So mostly we have, like, every block device is having some kind of file system. So most of the time we have to represent the buffer cache as a page cache. But if you read this statement, so it is saying the small amount of block data isn't file backed. That means we have to do some raw block IO operations on that particular device. So for that reason, we have to keep the buffer cache. Otherwise, we could have dropped the concept of buffer cache that I have already described how kernel can directly interact to the block device in the form of a block. So now we have discussed that we can do the read write operations on a page, like on a file or block device with the help of file IO or block IO. So there's we have the limited space or memory for the page cache. So like there will be time when we don't we no longer have the further memory to store the pages in the page cache. At that time we have to remove the pages, so that process we call it as the page eviction or page removal from the main memory, because our the allocation of page cache memory for page cache is limited. So at that time we will try to remove the pages that are not dirty. That means those pages are same as the disk. So like this is the page cache and this is the disk. So if page is not dirty, that means we have not made any modification on that page. So that page is same as the disk. So like this copy and this copy of the page is same. So we can remove this because it will not impact anything. Similarly, so when we want to remove a page, we have to find the clean page, not the dirty page. But situation can be that all the pages are already dirty. In that case, uh, we have to write a dirty page to the disk, and then we have to remove that page, because when we write a page into the disk, that page will become clean because both the copy in the page cache and the disk is now same. So let's now discuss how kernel decide which page to remove if we have some clean pages. So we will try to find the clean pages based on this strategy called it as least recently used pages. So the page, the longer it has not been used, it is the probability that it will not be used in the near future. So we will remove that page. So like here in the Linux, we use this to list strategy. So it is a modified LRU strategy. So here we keep active pages and inactive pages in the two different lists. So this is a head. So in the tail, we will push the pages, and from head, we will remove the pages. Okay. So same thing here. So like if we have accessed a page here and it is in the active list, if if like if we are accessing page 1, page 2, page 3, and this space is full, and the oldest page, so like oldest page we will keep it here inside this page because it is not accessed for longer time. And if that page, maybe let's say one page, if that is being accessed again, then we will keep it again inside the active list. So if you see here, the pages are moving between active and inactive list continuously depending on the use. So if we have some pages that is not accessed, like from a longer time, so it will be here only. So we have to remove that page from this inactive list. We never remove the page from the active list because active list says that these pages are recently used and it is a probability that these pages will be accessed again in near future. So when we like as we already discussed that when we don't have a clean page here to remove, then what we do, we write the dirty page to the disk. So writing the dirty pages to the disk, call it as a cache write back. So we have different type of cache write back strategies. So first one is no write cache, second one is write through cache, and third one is write back cache. So if you so like here in the no write cache, we don't write anything into the cache. We directly write and write the content into the disk. So the page present in the page cache, we have to invalidate that page. So here we need the page invalidation. So what is the requirement of the page invalidation? Like we say that this page is not valid inside a page cache. That means if we want to access that page, then we have to fetch that page from the disk. So invalidate says that it is not a valid page. So for to get the valid page, we have to fetch it from the disk. In the write through cache strategy, here is the pictorial view. So whenever we write in something inside a cache, then we also write into the disk. So it is a synchronized method to write anything inside cache and disk. So here we don't need to validate any pages because everything is latest as the disk because both are having the same data. And third one is the write back cache strategy. So here, like we are not continuously syncing that to the disk because it is a time consuming to sync into the disk. So there is no benefit of this cache, maintaining cache. So here what we do, like we do multiple writes on the pages inside a cache, and when later time, like there is a strategies when we decide to write back into the disk. So it is a better utilization of the cache, and like every time we are doing a small change in the page, we are not pushing it back to the disk. So we have a we have different strategies how to decide when to push the data from cache to disk, and that we will discuss uh, in the next slide. So these are the three situations, like when we have very less space inside the main memory, then we decide to push sorry, not in the main memory, yeah, in the cache you can say. So or or the dirty pages are very old. At that time also we push those pages into the disk, and we can also push the pages when some user space say that explicitly that we want to flush the pages of the cache to the file system. At that time, with the help of this sync and fsync system call, we do that. So so we decide that how much free memory we have at current with the help of this variable. If this uh, if this ratio is over the predefined value, then we have some mechanism like flusher threads. So these are the kernel threads. So we wake up those threads to do this job, to do these write backs. So those uh, flusher threads or kernel threads will do the write back into the disk. And we decide how old a dirty page is based on this dirty expire interval. So here this variable that says dirty write back interval. So if this is a regular or we say that periodic interval. So after every this amount of time, plus some threads will wake up and they will see if some pages are more than this time interval, they will push those pages to the disk or plus those pages to the disk. So let's now discuss about the laptop mode. So laptop mode is a special page write-back strategy, and its purpose is to optimize the battery life by doing less disk activity. So this laptop mode we can invoke from this configuration. We have to set it one, so it will become the laptop mode. It will come to the laptop mode, and this strategy is very useful when we have these two intervals that we have already discussed inside in this slide. So if these intervals are very long, at that time what will happen that our pages will not be, pages will be in the cache for a very long time. At that time we will have some block IO operations also. So here what we do that whenever flusher threads do the sync up of the pages into the disk, then at that time uh, other physical disk IO operations also will flush into the disk. So like here, what is the downside? Like we are keeping the dirty pages in the cache for longer time. So if there is some crash or power failure at that time, we can lose our data. So this is the disadvantage of this laptop mode. So this is all for this video. And let me tell you, like in the conclusion, we can say that we have discussed what is a page cache and how do we do the write back into the disk, and what is the buffer cache and how buffer cache and page cache are interrelated to each other, and how process address space access to the page cache to complete the execution of a program. And at the end, we have discussed about the flusher threads that do the page writebacks onto the disk. Those are dirty in the page cache. So that's all for this video. I will see you in the next video.